In this final set of comments on questions received, I'm going to address some subtleties regarding decidability and NP completeness. My first point is that single instances of a problem, that is, one input to a Turing machine, will always be decidable. But that decidability is technical, and it's useless if the underlying problem is really a hard one. And I was pleased to see that people are thinking how they could form a startup based on their solution to P equals NP. Here in Silicon Valley, we like to see people thinking that way. It's not just about intellectual challenges. It's about making the world a better place and getting rich while doing it. The first question from the forum concerns a doubt about my comment regarding Rice's theorem, that as a consequence of that theorem, it is impossible to tell whether a program does something specific, like a sort. Let's suppose we have a program that is alleged to sort an input list of integers. The questioner suggested that we can feed the program a list of integers, run it, and see whether the output is sorted. We could even feed the same program any finite number of lists, like 1,000,000 lists, in turn. It is true that if the program fails to sort any of the finite number of input lists, then you know it is not a sorting program. However, just because it sorts 1,000,000 inputs correctly doesn't mean it will sort the 1,001st correctly. I can give you several examples of bugs that only showed up in 1 out of 1,000,000 or more cases. The most famous is probably the Pentium multiplier bug, with a much tinier than 1 in 1,000,000 odds of it showing up on any given multiplication. But people were getting errors due to the hardware rather than the program. The point is that testing is a good idea. It does uncover most bugs, but that's still not an algorithm for deciding whether a program does what it is claimed to do under all circumstances. And in fact, there is no such algorithm. Rice's theorem proves that. It is worth remembering that problems, or their languages, are questions about an infinite number of instances. The answer to all, or all but one of those instances, may be no, but a solution to the problem still has to deal correctly with all possible instances. Single instances of a problem are always decidable, although we can't necessarily tell what the answer is. That is, suppose we have a problem represented by language L, and we ask if W, a single instance, is in L. There are two Turing machines, one of which answers yes, that is, it accepts any input, and the other of which answers no, that is, it rejects all inputs. One of these Turing machines answers the question, is W in L? Unless L is recursive, I can't figure out which of the two Turing machines answers the question. But I am absolutely certain that one does, and therefore the question, is W in L, is decidable. It has a Turing machine that always halts and gives the correct answer. Of course, this observation is useless, since we can't really solve anything with it that we couldn't already solve because the language L was recursive. The second question I would like to address is almost the same question, but regarding intractability rather than undecidability. The questioner hypothesized that they could invent an algorithm that runs in polynomial time and appears to solve some NP-complete problem, let's say SAT to be concrete. That is, they tested it on 1,000,000 expressions and it gave the correct answer in all cases. They then asked whether they could sell the solution to a company. The objective would be that the company would be able to solve problems quickly that no one else would be able to solve in less than exponential time, and thus could charge for the service. That's not quite the right approach. The right thing to do would be to start a company of your own, implement the solution, and sell the service. Once you have a business going, your company would be much more valuable than an unimplemented and untested idea. So you could sell the company for much more than you could sell the idea. You may, for example, have heard how Sergey Brin and Larry Page offered to sell the key ideas behind Google to Yahoo for $1,000,000, but Yahoo wasn't interested in developing the idea. Now Google is worth 10 times what Yahoo is worth. The second issue was whether you could keep the algorithm secret and still convince people that you had a solution to an NP-complete problem, and therefore to all NP-complete problems. That's not impossible, and we'll talk about it on the next slide. There's a fairly ancient theory called zero-knowledge proofs due to Goldwasser, Macaulay, and Rakoff Their techniques were motivated by exactly this conundrum. If you had solved P equals NP in the positive, and you wanted to prove to people that you had a solution without revealing your algorithm, could you do it? In the previous problem session, we argued that proofs of theorems require a social process where you reveal your proof to interested mathematicians, and they can examine and argue about anything that seems doubtful. Well, the methodology behind zero-knowledge proofs is also a social process, but of a very different kind. A verifier gives you many instances of the problem you want to solve, and you produce a solution to each but do not reveal them. You are then asked a question about each solution and must answer them all correctly to be believed. There is considerably more to the concept, however. Wikipedia has a good explanation of how a zero-knowledge proof works if you had a solution to the NP-complete problem called Hamilton's cycle. That is, whether a graph has a cycle that contains all the nodes exactly once. We just talked about being able to solve single instances of undecidable problems. The same idea applies to intractable problems as well. That is, suppose we have an NP-complete problem or language L, and we want to know in polynomial time whether a given instance W is an L. Since everything is now decidable, we can even run the non-deterministic polytime Turing machine and see whether W is an L. It will take us exponential time, but eventually we finish. And now we can design our polynomial time Turing machine to take input W and accept or reject whichever our exponential time analysis told was correct. This Turing machine can do anything it likes on inputs other than W. But as was the case for undecidable problems, this approach doesn't really help us. We can pre-compute the solution to any finite number of instances and use them in a polytime Turing machine, but that is not the same as solving the problem. Our, quote, solution is still useless for any instances whose solution we did not pre-compute. But let us return to the original question. Suppose someone came up with a polynomial time algorithm that they thought might solve SAT, but they couldn't prove it. Could they test it on, say, 1 million expressions and check that it worked well on all million? If so, wouldn't that be good evidence that the algorithm worked for any expression? Well, we have to be a little careful how the test expressions are selected. See, the easy case is if there were a satisfying assignment. That is, the answer is yes. In this case, we could expect the algorithm to provide at least one example of a satisfying assignment, which we could check easily and quickly. The hard case is when your algorithm says, no, there is no solution. There is no way known to verify that no is the right answer without checking the exponential number of possible truth assignments. That's not feasible for 1 million test cases or even one large test case. But perhaps we could handle this case if we knew that any expression that had a satisfying assignment had many such assignments. If that were the case, a randomized test would work. Pick a reasonable number of assignments and evaluate the expression on each. If any of them are satisfying, then your algorithm is wrong. But if none are satisfying, then you could conclude with high probability that your algorithm gave the correct no answer. Unfortunately, there are lots of expressions that have exactly one satisfying assignment. For example, consider what happens if you apply the construction in Cook's theorem to a deterministic Turing machine. There will be only one truth assignment, the one that reflects the unique computation of that Turing machine. I have enjoyed greatly the experience of using modern technology to present this material on the basics of automata theory to a worldwide class. Thanks to all of you who stuck with the difficult and challenging material. I hope it will have some good effect on your future careers, even if you aren't the one to prove that P equals NP. And I hope everyone who has come this far will do well on the final exam. As mentioned on the class announcements, the exam will be available for the 3-hour period of your choice during the week starting 11th of June. Certificates of accomplishment will be emailed to all whose total marks on the class are at least 50%, with the final accounting for half the marks and the homeworks accounting to the other half. Goodbye and good luck.